there's going to be two parts to this talk, one part which I'm going to talk about and one part which you'll see later. So the Cosmic Origins part is a 3D movie which we produced last summer, and at the very end of all the talks today we'll go into the room and you'll be able to see the movie and what it's about. But what I'm going to talk about now is the background to that, why we're interested in Stereo 3D and why you might be interested in Stereo 3D in the very near future if you aren't already. I'm currently head of the Innovative Computing Group at Durham University in the School of Engineering, and we also have the visualization lab there. Okay, so next slide. So we'll talk about three things today. First of all, stereoscopic 3D displays. What are they? What's the technology? Why are you interested in them? Secondly, why would you want to be interested in them? What are the benefits for people of viewing in Stereo 3D? And why might it change all the electronic devices in the world with displays on them? It has the potential to. And anyone who's read the numbers on Avatar, the movie, will have seen the billions of dollars that's brought to James Cameron. It's changed his life, I'm sure. And finally, I'm going to do a little bit of a slightly more technical stuff at the end with one equation in. So I'm not going to try and explain the equation to you, and you don't need to understand it to understand the implications of it. But a little bit about how you could go out and create high-quality content and actually build 3D display content, and why it's hard. It's quite hard. I want to try and get that across today. So first bit, Stereo 3D display technologies. Why they're happening now? Why are they of interest to us all? There's two driving technologies underlying this, and one is LCDs, flat panel displays. These are optically accurate devices which you can put other optics on top of and align really carefully with the pixels on every display. And this has given a huge impetus to the 3D display industry and has allowed 3D in many places where you wouldn't expect. And you may not know it, but Sharp, I worked at Sharp some time ago, for quite a long time, where we built a 3D mobile phone which sold over 3 million units. It failed for one reason, and the reason was that there was no one producing content for it. And these days now, that is possible. That'll all change. And the other technology that's changing in the cinema is digital projection. The digital micromirrors from Texas Instruments made a huge difference to what you can do in stereo in projected form. And we work very closely with one of the leading cinema systems producers, RealD, who delivered to us the first RealD system outside the cinema in our visualization lab in Durham. So it's these two technologies that are driving 3D. And what's the problem that 3D displays have to solve? We've all got two eyes. You have to get a different picture to each eye in 3D. So a screen like this one here you're seeing, it diffuses light, sends the same picture to everybody's eyes. Everyone sees the same thing. A 3D display has to become a directional device and drive a left picture to your left eye and a right picture to your right eye. And if you get the pictures right, just like in the real world, you'll see things leap out of the screen or go behind the screen, and it'll give you a 3D effect. So the display has to produce a directional element to it. One image to the left eye, one image to the right eye. What kind of choices are there for doing this? There's two at the moment, essential choices. One which is being commercially successful and one which might be in the future. So the stereoscopic approach, you use 3D glasses to separate these two viewing channels and give you a different image in each eye. Ooh, I'm back. And you can see President Obama here enjoying an advert at the Super Bowl last year in his home theatre at the White House, which everyone, of course, will have soon in their own houses, where he's using 3D glasses. And those glasses the projector sends out two images at the same time. The glasses act to separate out those two images so that only the left image goes to the left eye, the right to the right. This stereoscopic technology is where the commercial impetus is now. All the cinemas use stereoscopic technology of different types. Most of the commercial 3D TVs that have come out this January from Panasonic and Sony and Hyundai and LG, most of the big TV manufacturers, some kind of 3D glasses are used there. What everyone wants is what's on the right, which is the autostereoscopic 3D display, displays without glasses. Now you can go and buy them now, and there's an example here from a company called NewSight, their multi-view 3D display. And these displays typically send out more than 2 views at a time. This one sends out 10 views at a time, so that means that you can stand around the display and see any 2 of the 10 views and give you a stereoscopic 3D sensation with depth coming out of the screen and behind it. And they've found a small market in point-of-sale advertising like this famous razor company here, and that attracts people's attention in supermarkets and in hotels and airports. Of course, the interesting thing is that you can see the 3D razor on the shelf in 3D in full resolution next to it, but still the 3D display attracts your attention and helps them sell more razors, so that's great. So those are the technology choices. The Autostereo one, the reason it's not so successful yet is because it's lower resolution. But in applications where that doesn't matter, like the sales application, that's fine. If you want full resolution, full HD quality, you still need to go for the glasses. Okay, so that's the display technologies, stereo display technologies. Why would you want to use them? What are the reasons that the human vision system can benefit from them? Of course, you want to make a big profit if you're starting a company, but why would people be attracted to 3D at all? Oh, you'll see this little logo, binocularity.org. This isn't some kind of hypnosis thing. It's an outreach website we have where we try and explain for free some of the things we do. The free software tools on there for stereo. We give away things. So at Durham we have a kind of a pipeline for our research. We work very closely with the psychologists in human vision and human factors to understand how the brain works. And you'll see later on the Cosmic Origins movie, we try and produce demonstrators of what it's possible to do with 3D. And our core research is in algorithms for stereo 3D imaging and software tools. And in when Herb, I don't know if Herb's still at Codeworks, but maybe he is. Yep, some years ago now, Codeworks funded some research to develop one of our algorithms into a patent, which is now licensed to Wieldy, in fact, US company, and is being built into game systems. So we try, our core works there. But to build these methods for producing good quality images, we try and understand what it is about the brain that gives us a good 3D perception. So we can ask the question, why are some things easier to see than others? And in the brain, right at the back of the brain, on the right of this picture, is the visual cortex area V1. It's the first part of the brain that receives optical signals from the eye. That part of the brain responds to very simple features, and it will detect colour, it will detect size, orientation, so if things are at a different angle. Moving things, it's very quick to detect motion. Something's coming towards you, it's much quicker than if it's going away. It likes to detect tigers, and texture as well it's good at. But all those cues you could produce on a 2D display, the cue that it's very good at detecting you can't put on a 2D display is stereo 3D. And in the brain there are cells specifically evolved to detect stereo 3D. And on any 2D display, this one here, you're not using that part of your brain. So one of the reasons why I think stereo 3D is important for us is that it gives us a new pathway to direct information into the brain. You'll respond within less than 0.1 of a second to cues that we put up in stereo 3D. It's a very compelling effect, and it's because it's part of this visual cortex here, V1. So at a high level in the brain, what are the things that you will see in images when you look at a 3D picture? If you've seen a good quality picture, there's an awful lot of quite poor quality 3D out there, so beware of it. It'll make you feel somewhat uncomfortable. But one of the things you see very clearly is perception of depth relationships between objects. You'll very clearly see, for the 90+% of people who see in 3D clearly, you very clearly see a difference between my two hands in 3D. There'll be an air gap there. If you don't have 3D vision, it'll just be flat. You won't sense that volume, that space there. And that depth relationship is also known as a plastic depth effect. It's a very compelling thing for people to watch. If you've seen Avatar, you know when things come out at you, they look very differently positioned in space to things behind the screen. More subtly, the less well-known things, your brain's able to localize in depth. So if I'm looking at something in depth on a screen and I'm looking at, say, row 3 in the audience here, my brain stereoscopically isolates these people in row 3, you'll now feel embarrassed because I'm looking at them, out from the other things. And so if that's presented on a 2D screen, it's harder for me to do that than in 3D. So it gives you a way of separating information out on a screen. If you're in the military, it's great for picking out tanks. You can pick out a camouflage tank that you don't see in 2D. So you can see hidden visual detail, and a lot of the scientists who come and use our lab see things in stereo pictures they don't see in 2D pictures. If you're a product designer, it gives you a better perception of surface curvature. You want to see a car in 3D, you see a much better presentation in 3D of surface curvature. Or if you're designing kettles or water coolers or whatever you design. And finally, material perception is improved. If you have something like a metal or a gem, naturally it reflects light directionally, so different light goes in different directions. So if you want to get a good presentation of a metal surface, use stereo 3D and you'll see it'll appear more realistic in 3D, stereo 3D, than in 3D on a 2D screen. So they're at a higher level than the core V1 region of the brain, but these are all good reasons for using 3D. And we've done a number of studies at Durham in a number of different ways, some of them more popular with the students than others, on how you can improve task performance in 3D. And when we build 3D games like 3D Asteroids, people always get a higher score in 3D on a 3D screen than doing 2D on a 2D screen. So if you're playing a networked game, a 3D networked game, and you had a 3D screen, you would probably get a benefit from that. And the kind of size of benefit you get is 20 to 30% more from a high score point of view using 3D than 2D. The second task here is quite a complex path searching task. You may just be able to see that just there, and just at the back here there's two red spheres. You have to decide in this task if they're joined just by one of the grey spheres or not. And it turns out this kind of path searching task is quite common in many areas. The application that drove this for us was oil well planning with a company in Houston. Very complex 3D volumes of oil wells. If you want to plan a new path through that, 3D gives you a better, faster sensation of the 3D in there than in 2D. And in fact, this task is almost impossible to do in 2D. You probably, well, even if I blew this up to screen size, you probably couldn't do it. But you almost instantly can do it when you see it in stereo 3D. Okay, so a quick question at the bottom. Who thinks those two shapes are the same? Oh, good, we've got one guy who's on the ball tonight. So this is a mental rotation task where you have to look at these two shapes, in your brain rotate them and match them and see if they are the same. The answer is they are the same in this case. And it turns out that we've done trials, you can do these mental rotation tasks faster using a stereo 3D display and more accurately using a stereo 3D display than a 2D display. So if you're interested in people doing 3D tasks, manipulating or moving or connecting things, a 3D presentation, a stereoscopic 3D presentation, will give you a task performance benefit. Not twice as fast. You're getting two images. It doesn't go twice as fast or twice as better usually, but certainly 20 to 30% improvement in performance is common in the things that we've tested. So the other area where we've looked at how to get a benefit from 3D is in the application side. And at Durham, of course, we have some of the best cosmologists in the world. I'm very fortunate to have a guy called Carlos Frank, who we work closely with, who's one of the world's leading cosmologists. And we've taken some of his work and produced 3D movies of it for outreach to kids in schools. And initially via the Royal Society's Summer Science Exhibition in London in 2005 and 2009. And here we've taken our knowledge of how to produce good 3D pictures and put them into the movie as a way of attracting people to the science and of them understanding it. And these movies have been reasonably successful. Cosmic Cookery has been all over the world. It was on show in Mexico City for over a year in the Science Museum there. It went around the country to 10,000 school kids around the UK. And it won in 2006 the Visnet Prize for the best visualization of the year. The Complete Perseus was the similar one we did with Harvard. And then this year we've gone to an HD resolution movie, Cosmic Origins, which you'll see after the presentations today. And this was again designed to describe, the first one was about the large scale structure in the universe. The Cosmic Origins movie was about how galaxies form. And because this is a very 3D thing, I hope you'll see that it's better to see it in 3D, stereoscopic 3D, than it is to see it in 2D. Also because these are very abstract shapes. These are not things that you encounter every day that you understand immediately when you look at some of the parts of this movie. And that's, as was introduced earlier on, we're very lucky to win a prize in California just in January for this one. So that's kind of our outreach application. And as well as describing the structure, we found the children engage really well with this. We had a young kid at the last demonstration shooting the galaxies with his cowboy gun, which was much fun, as they whizzed past his head. So that's the kind of the background and the why, I hope. I'll begin to convince you why. One of the things with Stereo 3D, until you've seen it, you won't believe me, so you'll have to come and see it later on. So the question with 3D, and the question that's being asked quite a lot now, it's becoming more successful and more widely used, is how do you create high quality content, and are there any problems with it? Well, there are a few things I'll say, not too many, we've just got a few minutes left. The first thing is to say, if you don't have basically high quality images in the first place, you're not going to get high quality 3D out of it. So start with high quality 2D, because a lot of the cues that you use to judge depth in the world are entirely 2D. Texture and occlusion and aerial perspective and normal perspective, and you know how big sheep are, so you know how far away they are. You start off with a high quality for these. So then the thing that 3D adds is this thing called disparity. So here's a picture of the left and the right eye view of this orchid overlaid on each other, and I hope you'll see there's a disparity here. The same point, these are known as homologous points, but you don't need to worry about that. The same point in each image is separated by a horizontal difference, and the more of that horizontal difference you have, the more depth you'll see. So when you see the movie later on, when things fly up the screen at you, it's because they're just increasing the amount of disparity on the screen. It turns out your brain and your visual system are very sensitive to errors in that disparity. Small differences vertically or incorrect values horizontally will make you feel somewhat unhappy, or later on give you eye strain after you've seen 3D. So we spent a lot of time trying to understand this. This is the slide with the equation on. And this equation I left out of my last talk, but I put it up not because of the equation, but because of the things it tells us about why 3D is hard. So very quickly, there's a guy here, or a woman, a person, looking at the screen with their eyes a certain distance apart from a certain viewing distance. This is the screen disparity of the two homologous points, the left and right viewpoints. And when you look at these in your left and right eyes, you see a point in space behind or in front of the screen. In this case, it's behind the screen. And this equation just ties together all the variables in here. The consequences of this equation are that the amount of depth you see is proportional to the screen disparity here. The consequence of that is that you can't take a 3D picture on one screen and move it to a screen of a different size and expect to see the same depth in the image. And so a lot of people will take 3D pictures and get them tuned for a particular small screen size and put them on a big screen, and they become very uncomfortable. And that's because of this scales. Your eyes start to look outwards and it becomes unpleasant for you. Okay, so the other consequence of this is different viewing distances give different depth sensations. So people at the front of the room will see different depth to people at the back of the room. And this particular problem for 3D TV, for reasons to do with the focusing system in the eye, but again, means that images are not portable between different 3D displays as easily as 2D displays. So you can't just take a picture and put it on any display. You have to know the target display when you take a picture. And the final thing here, a lot less well known, is that it's inversely proportional to eye separation. So kids will have a smaller eye separation and will see more depth in the display, and will probably hit the limits of what's comfortable sooner than adults. And if you're creating content, games, movies, whatever it is for kids, but you're an adult, you need to test it with someone with small eye separation like a kid to make sure it's comfortable to use. So this tells us a lot of useful things about 3D, and it was first thought of written down by Helmholtz in 1867 and then long forgotten. But if you want to know why 3D is hard, that's some of the reasons. So I'll go through the last few slides quite quickly. So what we've done is taken our understanding and tried to build that into tools which help you use 3D more easily. And the way we've done it is say, well, we're gonna not talk about disparities and geometry. We're just going to say, on a particular display, you want a depth budget, a working depth range, and we'll target this working depth range as the volume or the scene. It's a bit like a theatre space. You have to fit the whole world into a small space that's not as big as the real world that you're trying to fit into it. And the reason that's there is because there's limitations with what the eyes can and can't see. And so we've come up with these mapping methods, which I won't say too much about, but we'll take a geometry of a camera and a scene that it's taking a picture of. As long as you can measure the depth in the scene, we have methods which will guarantee something about the quality of the depth within this depth budget on the 3D display. So we have tools which will calculate how to map scene depth to display depth in such a way that the final 3D pictures are guaranteed, in some sense, to be comfortable. And a lot of our work is about this. It's about how do you automate the process of taking a stereo picture to produce high quality at the end of the day. Tiny differences in the camera separation make big differences in what you see on here. And so if you get this wrong, it can be very uncomfortable afterwards. Okay, almost last slide. If you want to play with this on the web on binocularity.org, there's a free spreadsheet which sets up all the geometry for this, and you can test the different camera setups, the different scene setups, and different displays, and work out what capture conditions will work with your camera systems. Okay, so last slide. So 3D display technologies are becoming available on every device that uses an electronic display. You can get them for the iPhone, you can get them for laptop computers, you can get them for TV, you can get them for these size projection systems and cinema projection systems. They're becoming everywhere. I hope I've convinced you that there are some benefits of viewing in 3D. If I haven't convinced you yet, come and see Cosmic Origins later. It's entertaining, but it also has real measurable practical benefits. And if you want to produce high quality 3D content, don't just assume that you can set up 2 cameras where your eyes are and take a picture. It's not quite as easy as that. Okay, I'm done. Thank you very much.